Okay, blood flowing through an artery flows faster in the center of the artery, more slowly near the sides because of friction. Speed of the blood is volume equals C R squared. I'll get there eventually. R squared minus, I think, little r squared. Okay, millimeters. R is the radius of the artery. R is the distance of the blood from the center of the artery, and C is a constant. Suppose that arteriosclerosis, if I'm saying that right, is narrowing the artery at the rate of this, dr dt. Big R, that is. Negative 0.02. Find the rate at which a blood flow is being reduced in an artery whose radius is R is 0.05 with C is equal to 50. 500. Find, okay, they give us a hint. Find dV dt. Where, considering R to be a constant. Okay, so little r is a constant. Units of dV dt will be millimeters per second per year. What's that have to do with it? I don't see anything dealing with time here. Oh, this is per year. That matches per year here. Per second per year. Is there anything dealing with seconds? I don't think so. The reason why I'm looking, oh, here it is, per second. Okay, so everything matches. The reason I was looking is if this said per minute, that would be different. We'd have to modify it somehow. Okay, well, that's pretty clear, I think. We need to find this. So we're going to take the derivative. If I multiply this, actually it tells us what C is, but I'll get back to that. If I multiply C through, so we got C R squared minus C little r squared. Okay, now we want to take the derivative of everything with respect to t, where it's sitting. So we'll take the derivative with respect to time of volume. Is that volume? Yeah. And take the derivative with respect to time of C big R squared minus the derivative with respect to time of C little r squared. Now, we're taking derivative with respect to t, but there is no t here. So you take derivative like normal. Derivative of v is 1. But since these variables don't match, we put dv over dt. Whatever variable's in here goes on top, and then whatever you have down here, the dt, stays down here. Same thing here. We're taking derivative with respect to t, but there is no t, so you take derivative like normal. Take the 2, put it out in front, so we got 2c big R. But since it's we're taking derivative of the different variable than what's down here, we have to put our dr dt here. Now this is the part I'm not sure about. They tell us to treat the little r as a constant. Well, if this is a constant and this is a constant, the derivative of that would give us 0, so I'd drop away. Okay, so they also tell us little c is 500, so we'll plug 500 in for that. They tell us big R is 0.05, so we plug it in for that. And they tell us the rate of change of big R with respect to t is negative 0.02. In theory, we multiply that together, and that should give us that value. Of course, I didn't read the problem to see what they're even asking for, but 2 times beyond the initial. 500 times 0.05 times negative 0.02, negative 1. Geez, that comes out nice. Oh, negative 1. And that's how you work that problem.